Good morning and welcome to FOR 242. I am your professor, Dr. Neil Thompson. This is Map and LiDAR Interpretation. If you've had me in class before, you know you call me whatever you're comfortable with. That could be Neil, Professor, Dr. Thompson. Throw something at my head. Pretty hard to do from a distance, but give it a shot if you want. The class is asynchronous and online, spring 2021. We have got it set up so if you are an on-campus student, you can access the lab at your convenience. We'll set you up with building access. You can come in whenever you have time, whenever you want to set that schedule for yourself. There's going to be COVID-related ground rules about masks and all that, and some limits to capacity in the room. But we're going to have the labs available to you, and we've set up the old model school so that you can go to that place if the GIS lab is full. So you can go there, log in, do everything the same way as you would do if you were in the GIS lab. It just might be a little bit quieter for you. If you're off campus and don't plan to come on, QGIS can be downloaded for free. It is a free open source software. That's what we're going to use the most. My contact availability generally between 7 o'clock in the morning, 9 o'clock at night, sometimes a touch later. Snapchat is the quickest way to get in touch with me. My cell phone is just about as fast, and email I usually get to every half an hour or so. And you guys are my top priority throughout the semester, so whatever means of contact you're comfortable with, fire away. I will get to you ASAP. And the syllabus has all that contact information that you might need. Recommend going through it start to finish. As with all classes, that is the contract between myself and you. And that is a little bit different than it's been in past years. It's asynchronous online, where normally we sit together twice a week and do this for 2.5 hours. But we are going to do our best with this. I think it's the way it's been going for me so far. I think this might actually be an improvement. You can slow me down, you can speed me up, you can go back and watch me over again. You can go over these things as many times as you need to be comfortable with the information. So that is where we're at. This year, as past years, we have the dual goals of 1, getting you comfortable with maps, their interpretation, how to get where you're going, how to communicate your location to somebody else, how to communicate to somebody else where you want them to go. Basically, where to go, how to get there type questions. Second part of the class, LiDAR interpretation. What does that mean? LiDAR stands for light detection and ranging in the same way that sonar stands for sound detection and ranging, and radar stands for radio detection and ranging. All of these technologies work on the same fundamental principle that you have a pulse going out at a known speed. It takes a certain amount of time for that pulse to be returned to the sensor, and that is a measurement of distance. In this case, the thing is a laser, and the speed is the speed of light. We know that light travels at 186,282 miles per second, so if we sent a laser pulse to the moon, it would take 2.51 seconds to get there and back. That travel time is 2.51 seconds times the speed of light gives you 238,855 miles. And how, you rightly ask, does this apply to forestry? You put this sensor, which emits a laser pulse, or very many laser pulses per second, in an aircraft. That aircraft shoots the laser pulse down, and the returns give you the distance from the sensor to the foliage of the tree and to the underlying terrain. So the laser pulse penetrates the canopy in some places and fails to in others. So you get multiple returns from here and here, each of those giving you a distance to the sensor, which is in turn a distance off the ground. In concept, it looks like this. You have a forest canopy. You have your laser pulses coming down from the sensor as the aircraft flies over. Every one of those points is a return, measured in space. Has X, Y, and Z coordinates, so coordinate locations plus an elevation off the ground. Take that away and you have what we call the point cloud. That is the physical representation of the LiDAR as it comes straight out of the sensor. The result is a three-dimensional model both of the forest and the underlying terrain. So you can see these ground returns. That light tealish color down here, that is the ground or the terrain. Here we have the forest canopy of a tree with maybe 20% live crown ratio. So if you consider the total height and the length of the crown, about 20% of the tree's height here is live crown. This one has about 50% live crown. This is a very high resolution LiDAR data set. We can see returns off the trunks here. We can see a forest gap. We can see a second generation of trees here. Height being the major reflection of age. We have one age class up here, a second age class down here. We can see some understory trees that might be a third age class down here. We have a gap in the canopy. This could be trees, could be shrubs, could be another species. looks like we might have two different species going on here. This might be a sugar maple, this might be an aspen. Can't say from here. But you can tell an awful lot about the way this forest is structured. For instance, you might have a species that does beautifully in gaps. It could be a bird species, it could be a tree species, it could be a rare plant species. You'll be able to look for a gap like that and say, hey, if I'm looking for this thing, I'm going to look here. You might have something that builds its nest in the crooks of tall trees that have good cover around it. You might look for that there. You would look for a tree like this. This is a tree in a very good growing situation. About 50% live crown, tall, dominant tree above the main level of the canopy. You see a bunch of trees like this, you know you're in a good growing condition. You might look at a tree like this and say, these canopies are getting pretty bunched up. There's skinny trees. We might want to thin this out. We might want to give the growing space to this one, and this one by removing that one, that one, that one, and that one. The live crown ratios we can see here look to be about 30 to 40%. That is perfect for thinning. We have no live branches down below here. That means that once we give these trees room to grow, they're going to start growing faster, and they're going to put wood on these trunks, which are already well formed. And we can see they're already good and straight trees. So the branches have dropped off. It's going to form clear wood. It's going to be very valuable wood. So this little slice of life is great. We have trees in a good condition to do some treatment and give them room to grow, have a good sawlog production going there. We have older trees from an older generation. This one looks like it's going to grow great. This one's probably not growing very fast, but might have some ecological value. We have a gap here where we have probably regeneration. We have other species coming in here that are probably more shade tolerant. We have at least two species in the overstory, it looks like here, and we have a vigorous understory coming along here as well, reflected in these points. So this little slice of life has just about everything. We've just seen that we can manually interpret this point cloud, but when you have a point cloud for the entire landscape, the computer is trained to do that interpretation for you. The computer is looking for similar things. For example, the total height of trees. Very easy to measure from the point cloud because that's just the height of the highest return minus the elevation of the ground return. That gives you the height of the tree. If you know the age of the tree, that gives you site index. Site index is a reflection of the growing capacity of that site, essentially the fertility from the perspective of that tree species, where faster height growth reflects a better quality site. The length of the live crown is usually used to estimate the vigor of the tree. This one is going to be much more vigorous than this tree. These are likely the same age, and you can see this one has a huge trunk underneath. This one has a very skinny one. This has a very high live crown ratio. This one has a very small live crown ratio. That could be detected in the point cloud by a trained computer, and that can be used to reflect the growing condition of the entire site for the average live crown ratio throughout the entire collection of trees. Combined with a measure of crown radius, which is somewhat a reflection of the number of trees per acre, the amount of growing space allocated to each tree, then you have a way to calculate the entire volume of this canopy, length times width. That whole volume reflects the entire growing capacity of the whole power plant of the tree. And if you have this huge power plant up here, this huge sail up in the wind, there's got to be a huge trunk underneath this. This can't get to be this size without producing a whole lot of wood to support it. This one, in contrast, has a very small power plant and, likewise, a very small support system. If most of your trees, or if your average tree, has this large crown way up in the air, you can bet you're going to have a lot of large trunks holding all that up. Those large trunks, of course, are good saw logs, but they're also likely to have cavities. You're going to have good wildlife trees because a species that requires a large hole needs a large trunk to have that hole in. We can also look in the point cloud for gaps in the canopy. Those gaps could provide light for regeneration. They could be the result of natural disturbances like windstorms or bark beetle infestations or other causes of mortality, or it could reflect a recent harvest or a recent silvicultural operation designed to give trees more space to grow. We can also look in the point cloud, or ask the computer to look in the point cloud, if there is an understory horizon here, a group of trees that is growing beneath the main canopy. That could reflect regeneration from this parent cohort, or it could reflect other shrubberies or other understory plants. And we can also train it to look for those trees that are too small to cut that would get in the way of some other operation. Consider how this group of trees would look in a point cloud. You would have points all throughout these. The laser would penetrate this canopy, have multiple returns from throughout this foliated area, and you would have a very high live crown ratio. These trees on the edge, of course, have more crown than the trees that will be in the interior, and the point cloud will reflect that. Contrast those to these lodgepole pine in Alberta. The size of the crown here, we're down under 20%, some of these 15%. You can see these individual trees here are dying. These are tremendously unhealthy trees. This is the condition that is most vulnerable to the mountain pine beetle. There are patches of infestation all around this, and this is a very, very vulnerable condition. If you were dealing with an infestation, or trying to prevent one, you would use the point cloud to look for stands like this and look to correct the problem in whatever way you can. And if you couldn't do anything about it, you still want to monitor this situation because this is where problems are most likely to arise. Looking at it from the point cloud perspective, this is more like the first picture we saw. Large live crown ratio, wide crowns, regular spacing. This is in a pretty good situation for growth. Compared to this is, they're thinner, there's more trees per acre for sure, but the live crown ratio is still good. Perhaps time for a thinning. You give these trees more room to grow, their canopies will expand as they get taller, and you make some nice saw logs underneath here. Here we have a younger stand, it looks like. It's shorter. We have very long crowns here. They're skinny crowns. Some of these are bunched together. You see how these are overlapping. That could be time for a brushing treatment, but it's too short for a commercial operation. You couldn't make any money doing it by putting a machine in, so you don't try. You send a crew in with a brush saw, you give these trees room to grow, correct this issue, and then they have more space and the stand develops into more of a saw log potential in less time. In this point cloud, we see pretty regular spacing. We see decent live crown ratios for a thinning, maybe a touch past the perfection, but it's still within the window where it could work well. We have to be careful with this though, because these are pretty tall and whippy trees. They might be on the skinny side, they might be on the risky side. So you want to be extra careful to pick your best trees to keep, the ones that are least likely to blow over. And this is a higher risk situation. You're outside of the window where thinning is likely to be successful. You're more likely to have issues with wind throw, and these canopies are going to have a difficult time responding to the additional growing space given by thinning. What scientists are working very hard on right now is the ability to identify species from the point cloud. And here we can see several different species and their point cloud profiles. You can see how a computer could be trained to look for these things, but also how if you had a lower density at points, it would get kind of tricky to discern between E and G here. A and C, well, they're pretty different, but this looks like a lodgepole pine or a jack pine, which has a very sort of small, short, low live crown ratio. The live crown ratio is not necessarily a determining factor in species. This spruce has a very long crown. It looks like it's growing in the open, but you also have spruce where the canopy ends here. And how do you determine a spruce with a small canopy from a pine with a small canopy? It's a very tricky situation. But the very smart people are working on it. LiDAR has drastically changed the day-to-day work for foresters. Where before you were running around in the woods doing forest inventory on cruise lines, running a compass up and back and up and back and up and back, or maybe interpreting air photos to draw stand boundaries and then doing randomized plots within those stands. Now, instead of having a small sample of forest inventory, you have LiDAR data for the entire ownership. And for those companies that don't have it yet, they soon will, because there's publicly available LiDAR flights. The state of Maine has funded the collection of LiDAR for the entire state, and those data are coming online. Aroostook County is the last to get it because we're all the way up north. And we had some small issues with a very short window between when the leaves are off the trees and when the snow melts. So they missed some of that in the first year. They had to come back and recollect some data. And that is currently working its way through the system. For this class, you have data, some from public flights that were done on a smaller scale, and some data from a forestry company that has provided data from their private flights and their interpretation of those data, the computer-trained interpretation of those data, that you will get to work with to train with data sets that are very much like what you'll have everywhere very soon. So where before you would have been running all over the woods looking for things of interest, for merchantable wood, for streams that might have to be accounted for in a harvest plan, for buffers, for all those things. Now you're looking at a lot of these things on the LiDAR data, and then your role, instead of going to find them for the first time, is to go out and confirm them. That you think there's a stream here, potentially a vernal pool here, a very tall tree that might have a hawk's nest in it there, and you have a to-do list where you better walk out in the woods and you better go check on these things. You do not get to go and just do this all from a computer. This is still an outside job. But your role is now to confirm what the computer is showing you. That you see a spot here that's potentially risky, potentially a high slope, potentially this, potentially that, potentially enriched, potentially a wildlife habitat situation, potentially an issue with an old culvert that would pop out at you. All these things become your to-do list for confirmation, checking, and then what do I do about these things? So we're looking at this property. Maybe you want to buy it. Maybe it's just across the road from your professor's house and it's handy. We have a 2018 air photo. We happen to know this was last harvested in the winter of 2012. And wouldn't you know it, the federal government put a LiDAR flight in this region to sort of have a look at the Fish River and the St. John River, and we have LiDAR data from that. Let's look first at the digital elevation model. That is a raster model, meaning a data set where there's a series of pixels and every pixel has a value. That value in this case is elevation in meters above sea level. You see how this is changing as I zoom in and out? It's showing me the lowest elevation and the highest elevation whenever I change this screen. So that's the Fish River. That's a little tributary to the Fish River. This is a gravel pit. This is a road. This is the railroad bed. As I zoom out here, we see the road and the road. Let's turn that off, and you can see that's right where the road is. One of the first things we derive from the digital elevation model is the hillshade. The hillshade is a visualization of the slope and the terrain. In this case, it's a multi-directional hillshade, where a traditional hillshade, you can visualize it as shining a flashlight from 315 degrees, a little off from north, off to the left from north, and at an elevation of 45 degrees. Then you see shadows forming on the landscape. This is a computer-generated multi-directional hillshade which chooses, using an algorithm, one of 8 directions to put the shadow on. So you can see the road, where the road is built up here, where the road is cut in here. So you have a cut here and a fill here, so you took material from here, put it here, trying to make the road as level as possible. And then you can see this is a pile of building material here, road building material. Here's a little built-up hill area where a house is. Here's another way of making drainage happen around a house. So the house is here. This is cut in lower here, so it drains out here into this ditch and then across the road. This is another house building pad here. We can see where material was removed here and placed here, 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 and here for future use, and here as well. We can see the stream is cut in here. That may be natural, or this culvert here from the, I think this is the Bangor and Aroostook Railroad built around 1900. That may have concentrated flow and led to erosion here. We can see a ridge here, bit of a hill here, steeper ground here, but how steep, you ask? How steep is a question for the slope model, which is derived from the elevation model by asking what is the maximum change from each one of these grid cells to the next one. So here we can see the green colors are low slopes, red colors are high slopes, and yellow colors are somewhat in the middle. So we have some steep ground here. That again suggests maybe there's been some erosion or some movement. That's something to go check out there. So that would be on the to-do list of things to go look for if we were considering this property. We see higher slopes here. This is more likely to shed water and be well drained. We have lower slopes here. This is likely to collect water. Now, say we want soils data for this region. That can be accessed through the USDA Web Soil Survey. If I can spell it, there it is. The Web Soil Survey home, usda.gov, hit the big green button, and that'll take you to a map where you can use these zooming tools. Oh, we have a new version, lovely. And that zooming tool can take you, click, hold, drag, release a box here. That zooms you into the area of that box. Zoom again. Keep working your way down until you recognize where you are. Helps, of course, to know where you are, but I do. So here's our area here. And then we have to define an area of interest. And that is the area where we will be given the soils data. Click, hold, drag, release the box. And there's our AOI. That is the area of our soils map here, which we can look at on the web here. We can look and see there's MOB for that code, Monarda Burnham Complex. See that this is a poorly drained ground moraine here. So where does it say? Poorly drained soil. Foot slope, dough slope, ground moraine. And we also have some Thorndike here. Let's look at the Thorndike description. That's a very nice Channery silt loam. And it is farmland of statewide importance. It, I believe, used to be farmed. The neighbors say that this used to be a strawberry farm before these spruce were planted. And from there we can interpret some of the historical uses and where this is likely to be poorly drained. And if we choose to download that data, we can go to Download Soils Data, and let's see, create download link. That will generate a shape file, which we can then load into our map. Loading, 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 loading. Loading. There we go. Hit the zip downloads. Loading, loading, loading. Thank you. There we have our downloaded file here. We have to extract all. I'm going to place that in my C drive, GISNT. You cannot use the C drive on the lab computers. Those get wiped every time the computer shuts down, so you have to use your Google Drive file stream, which you can log into by going there if I haven't demonstrated that yet for you. But I'm going to go to GISNT, FOR242 datasets. This is the folder I have all these data in for right now, so I'm going to select that folder, extract, and that's going to unzip all of that. It was in a compressed format, and now it's not. So here we have our Web Soil Service, AOI 2020, spatial folder. And let's go ahead, and I'm going to place that there. I'm going to open up our December 27. And we can access that same thing here through C, GISNT, FOR242 datasets, December 27 photos, Web Soil Survey, WSS, AOI, spatial, and then we have the Soil MUA. I believe that's the one we'll want to use. Let's drag and drop that in, and there we have the same outlines. But let's go ahead and change how those are displayed. Click on the simple fill here. I want that fill color to be completely transparent. There we go. So now I just have the lines. Now these data are displayed on this map. I can click on this, and once that's done, I can use my Identify Features tool. I can click on any of those. It brings up the feature attributes. That MUSIM, M-O-B, Menarda Burnham Complex from before, appears. If I want these soil units labeled, I can double click here, go back in here, labels, and I want single labels. I want that label to be the MUSIM, and I can then choose what size text I want. I'll go with the default for now. So now we have the Howland, Thorndike, and Menarda Burnham Complex. You may have noticed that we have THC, THE, THD, and up here again THD again. Those correspond to different slopes. So TH is Thorndike, and the B's, C's, and D's, and E's all correspond to steeper and less steep slopes, where C is a lower slope than E. So A would be the lowest, E would be the highest one I see on this map. Let's go ahead and turn the labels off here. So double click, instead of single labels, no labels. And let's go ahead and turn on what I think is the most interesting data set we have here, and that is the canopy height model, which I have here in the clean format. I'm going to put that underneath there. And this is showing the brighter colors being the taller trees. And this is from 2012. So this is a snapshot in time. These trees have grown since. And that's where you can't trust LiDAR beyond its capacity. This is a snapshot in time. It's giving you very useful information. It's telling you how tall each individual tree is. At a 1 meter resolution, we can see gaps in the canopy here all the way to the ground with some small growth in here. We can use our Identify Features tool and see that band 1. That is a height of 11.69 meters. This one here, 19, 22. This spruce over here, 10 meters in height. All of this will have grown or died. So we don't know what's happened here since this time. Except, of course, that we do. So the job of the forester is to go out here, walk around, and see what the condition is. What has changed, what has grown, what has died. Are the streams where the elevation model thinks they are? Let's have a look. So here I have some photos. I can select those photos. I can ask it to show me those photos. The way I did this is I have a precise GPS location for each one of these points here, and then I use my phone's onboard GPS to get a very close location, which is often wrong. We'll see that when we get to that particular lab, which is why I used a high-resolution GPS. So I click on that, and up comes the photo. So that is a 360-degree panorama. So on my phone's app, I can start taking a panorama, spin in a circle. It keeps the phone level, so this is a level look at the entire situation. And we can use that to see what's going on here. So you see how that goes up and down and back up again. This is on steeper ground. So this, if we look at the slope model again, let's turn off that and turn that on. So here we are, there's higher slope. What does that look like? Well, there it is. That's the one we were just looking at. So that is what that slope looks like. But back to the canopy height model. Close that, canopy height model on. And let's see if we can interpret some things here. So we have a situation, this looks like it's right on the edge of this, we know it to be conifer plantation here. Let's have a look. And yes, so there's the big gap that we're on the edge of. We can see it at both sides. This, of course, connects to this, a 360-degree panorama. We can see we're on some slope here. And we can see we have an opening here and conifer here. Let's close this. There's what looks like a big gap, and lo and behold it is. So this is full of raspberry and looks like some red osier dogwood here. So we're in the middle of a big gap. We have an old apple tree here. This used to all be a strawberry farm. Now here's a bunch of tall trees. What do we expect to find here? Of course, tall trees. I see no gaps in this canopy. It looks like the last harvest might not have even gotten over this far. Let's take a look. Lovely cedar stand. This is wet, 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 wet. And there's braided ephemeral streams going all through this. There's some spruce here, but mostly cedar. A little farther down the way here, we have another photo point here, and this is a little more widely spaced cedar. We see some bigger trees and fewer of them. And we can also see some wet spots here and wet spot there. Now let's close that and keep moving around. So we see we're sort of on the edge of a gap here. Let's take a look. And so we are. So there's some aspen here. We're in an open spot here. We can see there's no trees right in front of the camera, but there is a patch up here. Again, old strawberry farm up this way. Close that. What else can we see? We have some openings in the canopy here. Let's see what the result of that was. We have some blowdown. That might have been what we're seeing in the canopy height model there, or that might have happened more recently. A lot of these look older. Some of them, like that one there, look to be newer. Let's close this again, and we can use this hand tool or pan tool to move over here. And let's take a look at this photo here. Right on the road, we can see same road, so where I'm standing is the pivot point on this 360-degree photo. So we're looking up the road and down the road in the same photo here. So all the way around, same exact road. We have conifer up here planted. We have natural regeneration here and here, more conifer here, more hardwood here. Look closely, you'll see a stream here. And if you look closely, you'll see a stream right here, and that's where a lot of the water is draining through. So let's close that. Let's turn off our canopy height model, because that's a bit of a distracting color. And let's turn on our contour lines. Those are derived from the digital elevation model through raster extraction contour. I'll teach you how to do that later. But this is showing every 1 meter of elevation, and that is reflecting the ditch along the side of the road. We have the road itself built up a little bit, and we can just barely make out some of that stream channel. And this is a tricky spot, so we really can't see very clearly where a lot of these stream channels are. It's bumping around a lot. They're braided channels, meaning they're flowing every which way, and sometimes above ground, sometimes below ground, sometimes down here, a more consistent flow, a perennial stream, where elsewhere it's an ephemeral stream that only flows after a melt or a rain event. But let's pop over across the way here and look at what's a more easily discernible stream channel. So where do we have a nice one here? Here's a good one. So this is where the stream has cut into the side of this hill. So flowing water has carved this out. You can see how that's a V shape pointing up the hill, where this more gradual U shape pointing down the hill, that's a ridge, that's a stream. Back over across the way here, I'm using the scroll wheel to move around. Let's take a look at this situation here. So select our tool, select what layer we want to be pointing at, it's already selected, and then let's take a look at these trees and compare them to the other trees that we saw. And this is of course not a formal inventory, not a stand-in for actually doing an inventory plot, but it gives you a lot of information, and you can also display inventory data for the same points. So the best situation would be to have your inventory data paired with some photographs that sort of remind you what you're seeing. Maybe you wish you'd recorded more information about the tree's quality, how many crooks you see, how many sweeps you see. The photo can help fill in those gaps. So let's close that. Let's take a look over here. We're seeing more skinny trees here. So there's a tighter spacing. Those two are right next to each other. These three are growing in the space where one would have done better. Those two are growing in a space where one would have done better. Those two, again, would have been better if there had just been one. Let's take a look over here in contrast. We have this area over here. Let's look at that photo. We'll see we have fewer individual trees, and each one of them is larger. That's, of course, an apple tree. Some of them might have too much space. This one growing right on the edge of this gap here has enough light that the branches are growing all the way down to the ground. It's going to create big knots and degrade the quality of the timber. This one forked into two trees. That's not ideal. This one doing pretty all right, some bigger branches. So of course you're balancing the need for smaller branches for a higher product quality with not having trees that are too ridiculously tiny to cut into a saw log at all. So here's more of a mixed species up here, up on the hill where it used to be strawberry and is now spruce. And let's take a look up here at our other stand across the way here and take a look at these trees. So here's a little wider spacing. This is really hitting the balance pretty well, I think. We don't have too many trees that are clumped in with one another. These here would have been better as one tree. This is one tree that forked into two. These could have been brushed out and thinned. That could have been removed. But these ones here, these are pretty good. So you have more trees of a higher quality and size here. This, again, a good happy medium. This one could have gone, but for the most part, we're looking pretty good in here. So the idea is to have all these things together. We have LiDAR data. We'll look at the point cloud for this later. It is a snapshot in time. It is limited in that respect. It is giving you a very, very high resolution of information at one moment in time. But it's also giving you this terrain information that is, for the most part, not going to change as quickly. You can have situations like a bit of a concentrated flow through here, took material from here, blasted it through here, and created a bit of an outflow plane here, and redirected some of the water into different places, where before it had gone through here, now it's sort of being diverted off either direction and flowing through the woods here. So the movement of water does change over time. But for the most part, the terrain is the terrain, unless you do something like this and move terrain from here to here to here to here for road building later on. So the terrain does change, but it changes a lot less than the overlying forest. And we can look at where the trees were at the time with a canopy height model. All of this gives you a to-do list. I want to check this out. I don't have any photos for here. This looks completely different from this. This looks like it may be, oh, what is it? Let's interpret our air photo here. This is conifer or hardwood. This looks like hardwood. So you see the difference in the color here between the conifer and this lighter color here, more likely to be hardwood. So let's turn on our canopy height model again. So we have taller hardwoods here. So you see we've interpreted this on the basis of the air photo and the elevation or the canopy height model. We have a big gap here. Might be nice for deer to browse in. This stand sees a lot of deer use, tracks and poop and other sign everywhere. We have trees that are shorter here, but we know they've grown in the last 8 years. We have trees all through here. We have gaps that are either filling in, or as the case happens to be, a lot of the poplar in here is dying. We have a lot of nice cedar in here. Again, spruce that has grown up since. Reasonably healthy condition there. And we have something to go check out here. So is that a natural erosion of this tributary, or has flow been concentrated through this very old railroad culvert? We have a road here. We have an interesting spot here where there used to be trees here, but there are no longer. So the canopy height model from 2012 is showing us that there's trees here. If we look at just the color infrared air photo, we see it's a farm field now. Interesting. How do we interpret that? We can pop over to Google Earth, which has some of the best imagery. We can access the look back in time feature here. Show historical imagery, that's the real name for it. See, here we have one for 2020, and we can go back in time all the way to 1997. So we see where these stands were established. We see that this area changes over time, so let's move it forward. We can see that angle is formed sometime around 2011, 2012. So there's 2011. There's 2012. Looks like they might have used that as a water diversion there. But let's look at this spot down here where there once were trees and now are not. So this is 2007, so you see I'm reading the years here, going back as far as 1997. Trees grow up, and then this field looks like it starts to get established. Looks like we have some solar panels gone in here. 2013 is a very good year for aerial photography in this region. For whatever reason, the resolution is very, very good. And then move forward, and now this is all being either maintained as yard or as a farmer's field. And this road has also been extended. So looking back here, no road, or maybe just a track, where we move forward, no road, and then somewhere in here, the road gets built. Unfortunately, we only go back to 1997 at this resolution, but it's still very, very good. We can see how this gravel pit develops, where in 1997 it was not there. And then we move forward, the gravel pit is developed, and the gravel pit grows. And you can see, if we zoom in here, there's one pile of road building material. Here's another, and there's some others sort of tucked away you can only see on the elevation model. So that's the class. We're going to be looking at all of these things in detail. I'm going to show you how to do them, how to make decisions, use all these different lines of evidence to guide your decisions, guide your fieldwork, how to connect your fieldwork to this computer system, how to interact between all these computer systems. So we have QGIS, we have ArcGIS, we have Google Earth. All these things can play together and should. And all these different lines of evidence, all these data types, all these photos and air photos and laser scans all come together to inform your decisions as foresters, as ecologists, as city planners, as somebody designing a road, where to cut and where to fill, as somebody looking for a spot to build, as somebody looking for a property to buy. All of these things come together into a decision support system. You still make the decisions, you still do the field work, you still confirm everything on the ground, but you have all this information at your fingertips, and we're going to teach you how to use it. Welcome to FOR 242.